Imagine a rapid release of industrial particulates venting into a dense urban canyon. Within minutes, the wind scatters the plume, and the physical evidence disappears. If a city relies on traditional environmental monitoring, this event effectively never happened. Fixed monitoring stations sit miles apart, and static mobile sensors follow rigid, predefined routes. The particulate release occurs entirely within the geographical gaps between those sensors. Even if a mobile sensor is scheduled to pass through that exact corridor, the rigid timing of passive collection means the plume fully dissipates before the sensor ever arrives. This failure happens because traditional monitoring relies on an open-loop architecture. The system collects data uniformly and passively, incapable of altering its behavior to react to the environment it is measuring. Open-loop systems are inherently limited by their sampling frequency. They are unlikely to capture high-variance events that occur outside their rigid spatial and temporal parameters. Tracking a constantly shifting atmosphere with a finite amount of sensing hardware presents a specific engineering tension. It is physically and economically impossible to place a permanent sensor on every square meter of a city. Addressing this challenge requires a transition from passive data logging to an active, closed-loop intelligence system. This is the framework behind Sparrow adaptive sensing. Instead of following a predetermined schedule, the Sparrow sensor fleet is actively directed by an AI-driven decisioning layer. The system continuously analyzes incoming data streams to determine where to measure next. When an anomaly or data gap is detected, the algorithms immediately dictate a change in the fleet's routing and coverage density, pulling resources toward the irregularity as it happens. This closed-loop approach allows the system to focus its finite resources on detecting and characterizing anomalies that traditional, uniform methods would likely miss. This diagram illustrates the Sparrow architecture. The system functions as a continuous, 5-stage feedback loop that interacts directly with a live city model. Stage 1 is continuous data ingestion. Real-time environmental data flows in from Sparrow nodes distributed across the target area. That data moves into Stage 2, pattern detection. Machine learning models parse the stream to flag irregularities, emerging hotspots, or sudden data gaps. Stage 3 is the decision engine. Algorithms calculate the priority of the anomaly and determine optimal coordinates for the next measurement. The instructions pass to Stage 4, the fleet optimization layer. The system alters the current node routes, directing them away from their previous paths to target the new priority zones. Finally, Stage 5 is focused measurement deployment. Multiple nodes execute high-frequency sensing precisely over the selected area, providing the detailed data that flows back into Stage 1. Through this continuous loop, the system responds to environmental events as they develop, rather than simply recording them after they have passed. In spatial sampling, treating all geographical areas equally is inefficient. Continuously oversampling environmentally stable zones yields little new information and primarily increases redundant data. Sparrow applies dynamic spatial resolution. It replaces uniform coverage with an adaptive grid, where stable areas merge into large blocks, and active zones subdivide into dense microgrids. By identifying stable areas as low variance, the system pulls sensing density away from them. This reduces redundant data collection in neighborhoods where the baseline rarely changes. The nodes freed from those stable zones are reallocated to high-variance areas, increasing sensing fidelity exactly where the environment is actively shifting. By collecting less overall spatial data in stable zones, the system yields a higher resolution digital twin of the areas that matter most. This architecture is necessary for capturing evasive events, such as short-duration emissions released in the early morning, specifically to avoid detection by standard monitoring schedules. A traditional sensor passing at noon will miss this. However, if a single Sparrow node catches a faint recurrent trace of pollution at 4 a.m., the pattern detection layer flags it as a priority. The decision engine then applies temporal targeting. Recognizing the 4 a.m. anomaly from day 1, it autonomously schedules a concentrated node swarm for 3:45 a.m. the following day to investigate. When the facility releases its off-hour emission on day 2, the vectored sensors capture and graph the localized spike from multiple points of origin. Deploying a sensor swarm to target a specific event provides a high-resolution dataset that confirms the origin and persistence of emissions that purposefully evade detection. Environmental baselines are not static. The origins of pollution evolve over long periods. In the winter, localized emissions are often driven by residential heating systems. In the summer, the dominant sources shift toward landfill emissions and microclimate heat pockets. Sparrow continuously recalibrates its sensing priorities based on these shifting seasonal patterns and historical trends. Effective environmental monitoring requires a system that is seasonally context-aware, ensuring the fleet allocates resources based on current temporal risks. When this closed-loop intelligence architecture is applied at city scale, the operational outcomes are quantifiable. Optimized fleet deployment eliminates unnecessary sensing coverage by greater than 30%. By removing that redundancy, every node yields a higher volume of actionable insights per hour of operation. This increases overall detection capabilities across a port or city without requiring the installation of additional hardware. Environmental monitoring is transitioning from passive mobile collection to a self-optimizing city-scale intelligence layer. Cities and enterprises can now allocate their resources based on actual, real-time atmospheric conditions. Sparrow Adaptive Sensing creates an environmental intelligence layer that focuses sensing capacity precisely where it is needed, in real time.